Once again, good morning, everyone. I had planned to spend the whole class going through problems on 3.7. I want to spend a second day on this lesson, although the setup, I think, is pretty straightforward using that framework. There's all kinds of ins and outs to these problems that we need to discuss. I'm going to do someone asked me if I would do number 21. I think what we did is we took a peek at number 21 last time. Welcome, Jen. We took a peek at number 21 in class yesterday, but we didn't finish it, and we plan to look at the complete number 21. And then I've picked out some other problems to do, but I still want to stay away. I mean, I did number 1 last time, and we're going to talk about 21. Those are both assigned problems. But I want to kind of stay away from the rest of the assigned ones and do problems similar to those. So that's the plan of attack. The first one I'd like to look at today is number 6. Number 6. So let's do that first. And I see our equation is y equals 1 over x squared. So let's write that down here. One plus x squared. Okay, and go back here. It says dx dt is 6. And then we'll do the first part. X is -2. Okay, so I mean, we got our variables x and y. We know, oh, and what are we supposed to find? Let's check that too. We are supposed to find, if you look up on top, it says find dy dt. So let me write that down. So dy dt, that's what we're looking for. Okay, now we've got everything we need. Relate the variables, that's already done with the equation they gave us. Okay, and so we can right away, I mean, we've already done the I, R they gave us, so it's time to go to the C part. Use the chain rule to implicitly differentiate. So, and we want to differentiate with respect to time. That's the new aspect to this lesson. So on the left, dy dt. And on the right, we have to use the quotient rule. So denominator times derivative of numerator, well, that's 0, minus numerator times derivative of denominator. The derivative of denominator is 2x. All over denominator squared. And then, because x is a foreigner, we also have to do dx dt. We have to do the chain rule. Because the inner function is, you know, inside of that original problem is still x squared. I mean, it's still an x. All right. Let's simplify that a little bit. So that first part's gone. On top we have -2x. On the bottom we have 1 plus x squared. And we got our dx dt over here. We also need what? I should have done the chain rule when it comes. Yeah. So the one thing I'm missing here is we should have taken the derivative of x squared too. So that would be a 2x. Okay. So now let's substitute what we know. We don't know dy dt. We know that x is -2, so that would be a 4 on top. -2 times -2 is 4. And on the bottom, we have 1 plus -2 squared. 2 times x is -4. And dx dt is 6. So if we simplify that, we get what? -24 times 4, which is 96. So we get -96 on top over 5. And that's supposed to be an equal sign there. That would be the end of number 6. Any questions? Okay, well, I wanted to go to number 18 next. So let's see what we have here. Number 18. Okay, so let me cover part of this up so we can take this part of the time here. Let's see, I'll fill that up. Okay, so a conical tank, so it's a cone with vertex down, is 10 feet across at the top and 10 feet across the top and 12 feet deep. So you can see my little sketch right here on the right. Let me make this a little bit bigger. So 10 feet across, that's another way of saying the diameter of the circle on the cone is 10 feet. And the water flowing in is 12 feet deep. So that's the height of the cone. All right. The water is flowing into the tank at the rate of 10 cubic feet per minute. So in effect, that's saying the height, dV dt, the volume is changing at the rate of 10 cubic feet per minute. So that's the dV dt on the left here that's given. We're supposed to find the rate that the height is changing. They call it the depth of the water, but that's this dH here. So dH dt, that's what you're trying to find. At the moment, the water is 8 feet deep, so H equals 8. And then in this problem, I actually figured out what R is, and that takes a little calculating to do. They didn't just hand that to you. Because if you look over on the right, let's see, where did I do this? Yeah, over here. Here, let's just do this on the side. So if we draw a right triangle representing, you can see I've got this depth thing here, this little circle. That's the height of the water at the current time, that little circle there, and its height. And that H is 8. So what you have is a little right triangle that looks like this. And that distance is 8. Okay. And so 8 is to 12. 8, the full height of the cone is 12. Okay. So 8 is to 12 as diameter. Okay, let me think about this. Okay, yeah, so the height is what? The height is 8 is 8/12, or in other words, 2/3 of the full size cone. So therefore, wouldn't the diameter be 2/3 of that? Except we don't want the diameter, we want the radius. So what's 2/3 of 10? 20/3, right? 2/3 of 10. Multiply 10 times 2/3 and you get 20/3. But that's the diameter, we want the radius. So what's half of 20/3? 10/3. So actually there was another thing given there, and I need that because how do you find the volume of a cone? Now, this one you might have to look up, but the volume of a cone is 1/3 pi r squared h. It's basically anything that comes to a point, the volume is 1/3. If this went straight down and it was a can or a cylinder, then it would be the radius, the base, pi r squared times the height. But because it goes to a point, it's 1/3. So you notice r is part of my equation. Knowing that, we actually calculated r. Okay, so now we've got our equation. Now we can redo this a little bit. I mean, what is r in terms of h? Okay, did I do this down below? Let me get rid of this. Yeah. Okay, so let me get rid of this now. So if you look at this figure at the bottom right, here's a picture of the original cone. All right. Diameter is 10, so the radius is 5. The height, as we know, is 12. So we've got this little right triangle, 5, 12. Okay. The radius is 5. The two legs are 5 and 12. So the radius is what? 5/12 of the height. Okay, so that little identity, r equals 5/12 h, I made use of in the equation up here. And I said, okay, in place of r squared, let's put its h name in, 5/12 h squared. Okay, so now let's go to the next page where I actually did the chain rule. Okay, I did that over here. Okay, so once again, I substituted in 5/12 h for r into that 1/3 pi r squared h formula. So here we go. I squared that 5/12 h. It becomes 25 h squared over 144. And then I just combined, well, if you take 25 h squared over 144 times h, you get 25 over 144 h cubed. And then if you just combine that all together, multiply all of that by 1/3, you get 25 pi h cubed over 432. So 3 times 140. So this is just a simplified version of everything put all together. Okay, so now it's finally time to do the chain rule on both sides. So we want to differentiate with respect to time. So on the left side, dv dt. On the right side, we would do the power rule. 3 times 25 is 75. Reduce the power by 1, so pi h squared. Otherwise, the 25, 432 is a constant. You can just leave that there, so I didn't have to do any differentiation there. Then I have to do the chain rule. I got to differentiate with respect to, I got to differentiate h with respect to t. So dv dt, if we look back to the original problem, where were we? You see dv dt was given to be 10, and r is 10/3. So I plugged in a 10 for dVdt, and I guess we knew H too. And what was H? H is 8. Okay, so I plugged in an 8. 8 squared is 64. And we're trying to find dH dt. Okay, so that's the only thing left. Then it's just a matter of a little bit of combination of things. And I finally got it down to, as I canceled and simplified things, I got dH dt down to 432 over 480, and then 480 pi, and then I simplified, and that gave me my dH dt, 9 over 10 pi. And the labels in the problem were given. We were, whoops, well, I should have locked that thing in. Anyway, the labels in the problem were feet, and it was per minute. So that's where I got the label from. So that one, a little bit messy, had to nail it down. So let me just go through what we did here. So the first part is getting a picture of this tank, a cone, and getting our variables set. They gave us that dVdt was 10. They gave us that H was 8. Right here it says 8 feet deep. And we went a little step further and found R. I'm not sure we had to, but we did. And then you had to know the formula for the volume of a cone. And this is one form of it right here. And so I could get one of the variables gone there. I substituted in place of R, we found its H value. And we did that using this picture on the bottom here. I mean, R is 5/12 H. So we substituted 5/12 H in for R. And then a little more algebra. We got it down to this black circle here. And then, all right, now let's differentiate both sides implicitly with respect to time, dVdt on the right side. So anyway, the rest of that is kind of just technical and doing basic algebra and arithmetic. Okay. Now, been scooting around a little bit on that problem. Does anybody want to talk about that one a little bit more? Or so I think, was that the one we? No, we did not do that one yesterday. Okay, that's number 18. Now we're going to go to 21. This is the one that we looked at yesterday. But any more questions on number 18? Okay, number 21. We looked at the setup of this yesterday. This is this moving ladder. Sounds really dangerous, leaning up against a house. And the ladder is sliding. It is this sliding down and sliding out as the arrows indicate. Okay, and the rate it's sliding away from the house down here is 2 feet per second. The ladder is, of course, a constant length of 25 feet. Okay. Basically, so we already talked about the 2 feet. How fast is the top of the ladder moving down the wall? What's this rate when the base is 7 feet? Yeah, and then there's 2 other parts, but we're going to just do the 7. So they told us X, this distance right down here, that's 7. Okay. We know that dx dt is 2 feet per second, so I wrote that down. And you want to know dh dt. How fast is the height, which I'm labeling as h? How fast is that changing? Okay, so I made a little picture here. I should have drawn the triangle the other way. But anyway, the height of the house, x is the distance away from the house, and the ladder length is 25. Well, what's the formula here? Well, just by looking at it, you should see it's the Pythagorean theorem. And so you look down, we have h squared plus x squared equals 625, which is 25 squared. So now we're set up. We're supposed to find dh dt, so let's get going here. So I solved this thing for, I moved the x squared over to the right, subtracted it, and I took the square root. So here is right at this point, let me get this. So right at this point, that's kind of where we're going to start. All I did was get h by itself. Why? Because we were trying to find dh dt. It makes it a little easier. Then when you take your implicit differentiation, dh dt is right by itself, which means we will be able to get to our result. So I wrote the square root as to a 1/2 power. So let's do the implicit differentiation. On the left side, dh dt. On the right side, we do the power rule, 1/2 times 625 minus x squared. Lower the power by 1. Chain rule, negative 2x. Chain rule again, dx dt. Because we're differentiating not with respect to x, but with respect to t. Okay, so algebra 1/2 times negative 2 is negative 1. So I get a negative on the top. And negative 2x times 1/2 is negative x. And this whole thing to the negative 1/2 power is a square root on the bottom. So I have the square root. I turned it back into square root notation. And dx dt is over here. Now let's plug in what we know. X is 7 and dx dt is 2. So in place of x, I plugged in a 7. Dx dt, I plugged in a 2. And down here, we can actually work it out. X squared is 49. 624 minus 49 is 576. And the square root of 576 turns out to be 24. And then just a matter of simplifying. 2 cancels into 24 12 times, and you get negative 7/12. The feet per second, you just come back and you look at your units in the beginning. We have feet and we have per second. So that's the rate at which the ladder is actually falling down against the edge of the house. So there's the rest of number 21. Yeah, I know that's a lot to take in. So does anybody have any questions? So in this problem, how do you relate the variables? Came down to a right triangle, and of course everybody knows the Pythagorean theorem. So I was telling you how when it comes to relating the variables, sometimes a real recognizable figure like this one, we all know the Pythagorean theorem. Sometimes it's the volume of a cone, like we had in the problem right before this. And you might even have to go looking up, you might even have to go look something up, possibly. But usually they're pretty easy to locate those. What about the parts B and C of 21? Okay, so now I'm not going to do that because the only difference in parts B and C is in place of x being 7, now you have x equals 15. Do the same thing with x equals 15. You just substitute in a 15 for x. And part C, or do I not have parts B and C? Here, let me look. What problem was that we were just doing? That was number 21. Okay, let's take a look. Okay, consider the triangle formed by, okay, well, yeah. All right, different problem. Part B. Consider the triangle formed by the side of the house, the ladder, and the ground, which is what we were already doing, right? So this time it says, find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So this time it's the area of the triangle. So we have a different relationship. What's the area of the triangle? What do you know about the area of a triangle? Oh yeah, base times height divided by 2. So now, instead of starting with the Pythagorean theorem, you're going to be using BH over 2. So, I mean, that's just a, so I'm not going to do it all over again, but that's just a matter of start at BH over 2. What's the base of the triangle? Well, what do they say here? It's 7 feet. All right, so that's 7. What's the height? And that would be using the, the same Pythagorean theorem. So, I mean, the rest of the problem is just yeah, actually there's 2 other parts to part A too. You see that? And that's when X is 15 and X is 24. So anyway, C says, find the rate at which the angle between the ladder and the wall of the house is changing. So now the angle between the ladder and the wall of the house. So that would be, let me try to draw this on here. No, I can't draw on this picture. So let me go back. Yeah. I don't have the tools to do that, but that would be this angle right where my mouse is. I don't know, can you see my little cursor there? That would be this angle right in here. And now you might have to use what? Some trigonometry? Because you know this distance, you know this distance. What is that? That's the side opposite over the side of G. So that would be a tangent problem. So you would say tangent of that. And then you differentiate that. So it's just a different equation to begin with. And then just follow your, what do you call them? Your implicit differentiation rules. Differentiate both sides with respect to t. What's the derivative of the tangent? Oh yeah, the secant squared. And okay, let's take a look at number 34. Number 34. Okay, let's first just take a look at it here. I can't make it any bigger, but it says electricity, the combined electrical resistance R of 2 resistors R1 and R2 connected in parallel is given by this equation. 1 over R equals 1 over R1 plus 1 over R2. And R1, R2, and R are measured in ohms. Okay, and then they give you some given information. All right, now let's go to the problem. Number 34. Okay, so there's our equation. 1 over R equals 1 over R1 plus 1 over R2. We are given that dr1 over dt is 1, dr2 over dr2 dt is 1.5. Resistance 1 is 50, resistance 2 is 75. So all of the material above the red line, well, including this, is given. Okay, there's not, that's just all that stuff on the top that's been handed to you. So we're going to take, we've got the equation. So here's a case where you don't have to search for the equation. They just handed it to you. So now we got to do the derivative of both sides. What's the derivative of 1 over R? We got to use, I didn't show it, but you have to use the quotient rule. So denominator times derivative of numerator. Derivative of numerator is 0 minus numerator 1 times derivative of denominator 1. So negative 1 on the top over denominator squared. So does everybody see that? So I don't have it all written out, but that's a quotient rule that gets me to that point. And then, of course, we've got to do the times the derivative of r with respect to t. On the right side, same thing. Negative 1 over r1 squared. And then we have dr1 dt plus, and then over here, same deal, negative 1 over r2 squared dr2 dt. Now let's start plugging things in. Okay, r is 30. So r squared is 900. 30 times 30. So, and that's times dr dt. By the way, what are we trying to find here? We're trying to find dr dt. I should have written that down. So let me put that on here. So you're trying to find dr dt. Okay, that's also part of the problem. All right, so on the right side, just substitute again. What's R1? R1 is 50. R1 squared is 2,500. We do know dr1 dt, and that is I'm sorry, dr2. This is dr2 here. Hang on. I got to just check here. What am I doing? So r1 squared, that's correct. Anyway, it's just a matter of substituting, and then basically the rest is arithmetic. And so the key here is I had to use the quotient rule 3 times in the beginning. So a review of differentiation. Oh, and then we got to remember you got to use the chain rule in each variable, and R1 and R2 are separate variables. So you gotta just kind of follow through on the rest of that. All right. So let's look at one more problem. All right, let's take a look at number 25. This is another one of your assigned problems. So I'm going to be handing you another one that you have to do. Okay, so let's go to number 25. So let's first find it in here. 25. So 25 uses the figure on the left here. An air traffic controller spots 2 airplanes at the same altitude converging on a point. So in other words, they're heading for a collision as they fly at right angles to each other. See figure. So I don't know if you can tell, I have a little bigger version I can show you, but this plane is flying south. And this plane down here is heading east. And they would converge at this point right here if we just let them fly. All right. One plane is going 225 miles an hour, and the other one's moving at 450. Oh, one plane is 225 miles away and is flying at the rate of 450 miles an hour. The other plane is 300 miles away and is flying at the speed of 600. At what rate is the distance between the planes, that's this diagonal, how far are they actually apart from each other? At what rate is that distance decreasing? So that's the problem. Okay, so now let's take a look at this. So this picture is a little bit bigger. I'll blow it up so you can see it better. So you see this plane is heading south and is at the distance of 300 miles. The tip of the plane is at 300 there. It's 300 miles from where it would collide, and it is heading at a speed of 600 miles an hour. Why did I write a negative? Because it's going downward. It's decreasing at the rate of 600. That was given to us. And this plane is at 225 for a distance, and its rate of speed is 450. Negative because it's going left, moving toward the negative. So I called this one y and this one x. And of course, obvious equation here is the Pythagorean theorem. S is the what? The actual distance between the two planes. So I can write that down. We know how to do that. That's s squared equals x squared plus y squared. Good old Pythagorean theorem. So all of this is given, and we want to find ds dt. At what rate is this distance s decreasing? So there's our problem. All right. So now let's start to work on this. So I rewrote the square root. S equals square root of x squared plus y squared. I wrote it in this form. S equals x squared plus y squared to the 1/2 power. So there's our relationship between the variables. Now it's time to differentiate with respect to time. So on the left, ds dt. On the right, first power rule, 1/2 times the quantity, x squared plus y squared, reduce the power by 1, negative 1/2. Do we have a chain rule to do? Yeah. What's the derivative of x squared plus y squared? Well, first of all, it's 2x, and then dx dt plus 2y dy dt. And all of that is being multiplied. Okay. So then just some algebraic simplification. Again, we've got our 1/2. We just left that be. And we put this under a square root sign on the bottom because it's to the negative 1/2 power. All right, that's all I did in that step. Now, substitute stuff in. So for that, we got to look up at the top here. So in place of x, you're going to plug in 225. In place of y, you're going to plug in 300. And then when it comes to dx dt and dy dt, we've got those given up here too. So then it's just a matter of plugging and cranking. And it turned out they're approaching each this distance is decreasing at a rate of 750 miles an hour. So in other words, wow, you don't have much. I mean, that's much faster than the planes were traveling. Well, it's faster anyway. They're approaching each other at a great rate of speed. So if they're coming at each other at 750 miles an hour, let's see, that was part of the rest of the question. Let me go back and find, what's the question? Yeah. So we found the rate at which the distance of the planes is decreasing, 750 miles an hour. How much time does the air traffic controller to get one of the planes on a different flight path? Well, so how do we figure that out? Okay, let's go back to the problem. Well, so why does he only have a half hour? Well, half of this is what? Half of 750. I mean, that's 750 per hour. A half hour would be what? Half of 750, which is 375 miles. I'm sorry, 375. Yeah, 375. Well, I mean, 375, the planes, I mean, this plane is only 300 miles from the collision zone. So if you wait until, I got to think about that one. Why is it a half hour? Yeah, because this plane is only 300 miles. This plane right here on the bottom is only 300 miles from the collision point. So, I mean, if you wait a half hour, 375 miles, they will have already collided. So you don't have much time. You got to move quickly. So there's a good example. Again, what was the thing that related the variables? It was the Pythagorean theorem. So something big like the area of a circle, the area of a triangle, the Pythagorean theorem, maybe the circumference of a circle, something that you would have had in your past is what relates the variables. So that part of the problem shouldn't be too difficult. So let's see, where did the negative 2x come from? What problem are you on? What problem was Rachel? I'm sorry. I apologize. It's hard for me to watch all these different places. Yeah, so that you did figure it out. Okay, good. Awesome. So, other comments or questions? And you can just speak up. It'd be good to hear your voice too. That way I can't ignore you accidentally. So let me just make a comment too. I had stated sometime in the past that we would have an announced quiz, and we're going to do that yet. But I'm going to wait. So what we probably will do is tomorrow we're going to have more. We're going to have more of these to talk about. And I'll talk to you. I'm going to tell you that we're going to have a quiz then on Friday. So I'm telling you that right now. We're going to have a quiz on Friday. And I'm going to tell you what it's on, too. It's on just all the types of derivatives that we now know. So, for example, you got to know all your basic rules like constant rule, the power rule, the quotient rule, the product rule, how to take the derivative of a logarithm, how to take the derivative of a natural log, and how to take the derivative of a constant to a power. All those things. See if I can find it. I don't have a copy of the book, but I've got so on my book, it's on page 179. Let's go back and let's try to find it. Okay, what page are we on here? 186. So let me just go back a little bit. Should be in 3.6. There it is. So it's at the bottom of page 177. I mean, that summary right there is what I would give you a quiz on, and we'll talk about that a little bit more. There's trig derivatives there. I'm not going to do the inverse ones on the bottom, number 19 through 24, but you should be able to do trig identity. Anything above, anything above number 19, 20, 21. That I would draw a line there. I can't do that at this time. But all the types of derivatives are those first 18 there. And just do you know how to do a derivative of each one of those types? That's what we're going to have a quiz on. And we'll do that on Friday. And we'll talk more about that in class tomorrow. Okay, questions? All right, then I think we're going to hang it up. Thank you. I appreciate it. I will see you tomorrow.